Have you noticed that in many Indian cities, the heat feels completely different now?
Oh, absolutely. It's a very specific, almost heavy feeling.
Right. I want you to really think about that visceral feeling for a second.
Yeah.
It is not just that it's hot in the afternoon. It is this heavy, oppressive heat that lingers in the streets.
Yes, it just stays trapped.
Exactly. Trapped through the entire night. And it builds up alongside this dense pollution that makes simply breathing or walking to the store feel completely exhausting.
That physical weight you're describing is incredibly specific, and it's something millions of people are experiencing right now. We aren't just looking at numbers on a thermometer anymore.
No, not at all.
It is a fundamental shift in the atmosphere of these cities.
And the mission of our deep dive today is to understand exactly why our urban environments are turning into these thermal traps.
Right, because the old solutions just aren't working.
Yeah, we are going to look at why the traditional fixes we always hear about just aren't cutting it, and how concepts like urban green corridors and biophilic design are essentially our best blueprints for building cooler, more resilient cities.
They really are.
Okay, let's unpack this because we are pulling from a massive stack of recent meteorological data, public health reports, and urban planning case studies today.
And to properly digest all that data, we really have to reframe the problem. The consensus across these reports suggests we are not just talking about a temperature issue,
Right, it's bigger than that.
much bigger. What we are looking at is an overlapping crisis of public health, air quality, and urban governance. All of these things are colliding on the very streets you walk on every single day.
So before we can talk about fixing the city, we have to understand the invisible physics of how it currently operates.
Exactly, the foundation of the problem.
And the root cause here is what scientists call the urban heat island effect. Basically, we have systematically replaced trees, lakes, and open ground with asphalt, cement, glass, and metal.
And those materials fundamentally alter the microclimate. They have two major physical flaws when it comes to managing the environment:
Which are?
low reflectivity and extraordinarily high heat retention.
So they aren't bouncing the sunlight away. Their surface albedo is so low that they are just soaking up solar radiation like a sponge all day long.
Precisely. But that absorption during the day is really only half the battle. The real issue is their thermal mass.
Meaning their ability to hold on to that energy?
Yes. As the sun goes down and the air tries to cool, all that concrete and asphalt slowly releases that stored heat back into the environment.
I see.
That continuous release is why dense city centers remain so incredibly warm long after sunset. The physical environment simply will not allow the air to cool down.
It's like the modern Indian city has been turned into a giant cast iron skillet.
A cast iron skillet, that's a great way to put it.
Right. You know how you cook with cast iron? You turn the stove off, the sun goes down, but that pan is so dense it's going to stay burning hot for hours after the heat source is gone.
The thermal physics of your skillet analogy are spot on. If we connect this to the bigger picture, imagine that skillet is constantly being reheated by friction on the surface.
Friction from what?
Well, it's not just the sun. You have to add in the ambient heat generated by intense traffic, the exhaust from millions of engines, constant construction activity,
Oh, wow, yeah.
and overworked power systems, venting hot air from air conditioners. Combine all of that with poor ventilation between tall, dense buildings, what urban planners call street canyons, and the air literally cannot move.
So the city behaves exactly like a thermal trap. But the meteorological data points out that this gets even more complicated and honestly way more dangerous when the seasons change.
Right, the winter crisis.
Yeah, the cast iron skillet doesn't just trap heat.
When winter arrives, many Indian cities face a severe crisis with air pollution, specifically PM 2.5.
Those are the ultrafine particulate matter drops.
Exactly. Small enough to bypass your body's natural defenses and enter deep into your lungs and bloodstream.
The connection between the heat and the winter smog is what really jumped out at me in the sources. The exact same urban form that traps heat in the summer acts as a physical trap for pollutants in the winter.
It creates a thermal inversion layer, essentially a dome effect.
Like a lid over the skillet.
Precisely. When visibility drops and that thick smog rolls in, the cold, polluted air is held in place near the ground by the physical structure of the city, and a layer of warmer air above it.
Wow.
You aren't dealing with an isolated heat problem in the summer and an isolated smog problem in the winter. You are dealing with a year-round structural flaw that creates overlapping exposures.
Overlapping exposures. I mean, that sounds like a public health nightmare waiting to happen.
It is. The public health reports make it abundantly clear that heat stress and air pollution together create an incredibly dangerous combination.
And it hits certain people harder than others.
Definitely. It takes a massive toll on specific vulnerable groups. Children whose lungs are still developing, older adults, pregnant women, and people with pre-existing respiratory or cardiovascular conditions.
And we absolutely cannot forget outdoor workers.
Right, people who don't have the luxury of escaping into an air-conditioned room.
Looking at this data, it's just obvious to me that this isn't just an environmental issue. It proves why city departments can't operate in silos.
Yes, exactly.
I mean, if the street layout is trapping both the exhaust from the transit department's buses and causing the health department's asthma spikes, they are essentially fighting the same enemy.
Fragmented thinking guarantees fragmented solutions. The urban planning case studies heavily emphasize that we have to treat transport, land use, and public health as one single interconnected system.
Which brings us to the solutions we usually try. If the city is a cast iron skillet trapping heat and pollution, the logical next step is to cool it down.
Right.
But I have to push back on the sources here, acting on behalf of anyone listening. Wait, aren't we always told to just plant more trees, build more parks?
We hear that a lot, yes.
My local park has hundreds of trees. Are you saying it isn't actually helping the city?
Well, green space matters immensely. Let's be clear about that.
Uh,
But the traditional default solution of simply carving out a square block and calling it a park is failing to cool the wider streets.
Why, though? If I walk into a large park on a hot day, the temperature drop is incredibly noticeable. The trees are clearly doing their job.
They're doing their job within a very strict boundary. In the context of a sprawling concrete city, a park acts as an isolated island of cooling.
Okay.
The cooling effect, what we call a microclimate, has an edge. Once you step out of the park and walk half a block down an asphalt road, the ambient temperature spikes right back up. The park fails to change the thermal behavior of the wider city because its influence doesn't travel.
The edge effect, so it doesn't project that cooling outward through the concrete.
Think about your daily life and your typical commute. That isolated park likely fails to reach the routes you use every single day.
True.
Does the cooling effect of that park reach your child's school? Does it reach the bus stop you wait at? The market? Usually the answer is no.
Yeah, usually I'm standing on a hot sidewalk.
Exactly. It doesn't improve airflow or reduce pollution exposure across the vast stretches of built-up districts where people actually spend their time.
So having a beautiful, lush park 3 miles away doesn't stop you from breathing in PM 2.5 or suffering heat exhaustion while you're waiting for a bus on a concrete median.
That isolation is the fatal flaw. That is why the planning journals advocate for a monumental shift in how we think about urban greening. We must move from isolated green patches to urban green corridors.
Let's define that. How does a corridor physically behave differently than a park?
An urban green corridor is a continuous ecological pathway that weaves through the city. Instead of a blocked-off square of nature, it connects the city's infrastructure.
So it's not isolated.
Right. It networks the streets, the water bodies, the public transport routes, and the neighborhood spaces into an unbroken chain of vegetation.
It's taking the microclimate of the park and stretching it out along the paths where people actually live and move.
Furthermore, it's about multifunctional performance. A well-designed corridor does several things simultaneously.
Like what?
It provides continuous shade, cutting off solar radiation from hitting the asphalt in the first place. That cools the surface temperatures. Importantly, the linear geometry of these corridors creates channels that help wind move more effectively through the city.
And that wind actively flushes out particulate pollution.
Exactly.
Now, the sources also brought up a really interesting psychological and architectural concept here called biophilic design. How does that fit into these corridors?
Biophilic design is the concept of integrating nature and natural patterns into the built environment. It's driven by the biological fact that humans are wired to be in nature.
Right.
It's not just about throwing a potted plant in a lobby. It's about designing streetscapes and building facades that incorporate natural light, flowing water, and vegetation, because it demonstrably lowers human stress and improves cognitive function.
So when you build a green corridor using biophilic design, you drop the physical temperature, you clear the air, and you lower the mental stress of the commute.
Exactly.
Suddenly, active transport, like walking or cycling, actually becomes viable again. You aren't forcing people into cars just to survive the heat, which in turn lowers traffic and exhaust.
You've just described the ultimate positive feedback loop. Green space in a city shouldn't just look pretty. It must function as critical climate infrastructure. Performance over aesthetics.
But how do we actually engineer that?
Yeah.
Because planting a row of sad saplings on a concrete median strip clearly isn't creating this biophilic cooling feedback loop.
No, it really isn't. It requires precise design and a deep understanding of urban mechanics. This isn't just a landscaping task, it's a design science.
I notice the sources get very specific about the engineering here. For example, you can't just pick any tree, you need the right vegetation. Why does this specific type of plant matter so much?
Because not every plant performs equally when it comes to cooling. Some trees have wider canopies for maximum shade, but more importantly, plants cool the air through a process called transpiration.
That's when they sweat water vapor, right?
Yes, essentially. And that water vapor cools the surrounding air. You need high transpiring plants that can survive urban smog. Then you need proper spacing and airflow-aware street geometry.
Meaning you can't just build a dense wall of trees that acts as a windbreak, stopping the breeze from flushing out the PM 2.5 on the street level.
Right. The physics of airflow dictate that buildings and trees must be positioned to channel wind, not block it. Next, you need permeable ground surfaces.
Here's where it gets really interesting, at least to me. Instead of sealing every square inch of ground with cement, the surface needs to be able to breathe. How does a permeable surface actually cool the air?
It comes down to evaporative cooling. Permeable pavements allow rainwater to soak into the earth below. When the sun hits that surface later, the stored water slowly evaporates. As water turns from liquid to gas, it absorbs latent heat from the surrounding air, naturally lowering the ambient temperature.
Wow.
Solid concrete, on the other hand, just forces the water into a storm drain and then bakes in the sun.
It's important to note here that while city councils debate the cost of overhauling this infrastructure, the reports highlight a massive equity issue. The burden of this heat and pollution is not distributed equally at all.
Not even slightly. The data shows a stark divide. People living in informal settlements, in roadside housing, or in heavily dense neighborhoods with poor ventilation face the absolute highest exposure to these elements.
And they possess the least protection.
Exactly. They can't just retreat to a climate-controlled high-rise.
So designing these corridors isn't just a luxury upgrade for a wealthy neighborhood. According to the urban planning studies, a cooler city is fundamentally a more just city.
It creates a healthier, more equitable baseline for everyone. And we know this level of engineering is possible because we have global precedents. Other cities are already showing us the blueprints.
The sources highlight a few incredible international examples. Singapore, for instance. The reports say they have basically integrated greenery as the city's operating logic.
Yes, Singapore utilizes aggressive vertical planting and sky gardens. But the crucial lesson there isn't just to plant more trees on balconies.
What is it then?
It's that nature is engineered into the very fabric of the buildings and streets from day one. Buildings are structurally designed to hold massive amounts of soil and water, with irrigation systems cascading down facades to cool the ambient air before it even reaches the street.
That is amazing. The example that really caught my imagination was China's sponge city approach. That term paints such a vivid picture. How does a city act like a sponge?
What's fascinating here is that it's a shift away from traditional gray infrastructure.
Gray infrastructure being like massive concrete pipes and storm drains.
Exactly. A shift from that toward green-blue infrastructure. Instead of treating rainwater as a nuisance to be flushed away instantly, a sponge city uses interconnected bioswales, retention ponds, and permeable roads to catch the water.
So it absorbs the environmental stress. The water slows down, sinks into the ground, filters through the root systems of the urban vegetation, and then evaporates over the following days to cool the area.
The city is engineered to work with the environmental pressure, rather than fighting a losing battle of resistance against it. We also see holistic integration in places like Curitiba, Brazil.
Right. Curitiba is famous for integrating their transport planning with their environmental planning. They didn't have one department building a bus lane and another department building a park completely blind to each other.
Exactly. When Curitiba built their famous bus rapid transit system, they deliberately zoned high-density housing along the transit lines, but they turned their flood-prone river basins into massive linear green parks instead of concreting them into channels. The transit moves the people, and the parks manage the water and the heat. It is the overarching lesson from all these global blueprints. Cities become resilient not by accident, but by deliberate, integrated design.
Deliberate design is great in theory, But, anyone who has ever attended a city council meeting knows that real-world urban governance is made of messy, overlapping bureaucracies.
Oh, definitely.
The transit authority isn't talking to the parks department, and neither is talking to the health board. So how do local governments actually execute a green corridor?
Bridging the gap between architectural theory and street-level execution is always the hardest part. The sources highlight organizations like Sustainability Alternatives that work precisely at this intersection, trying to force multi-departmental coordination.
And it seems daunting.
It is, but the urban planning journals lay out a very clear, sequential six-step blueprint for cities to undergo this transformation.
Let's walk through that. If a city decides they want to fix this, they obviously can't just dig up every road at once. Where do they even begin the surgery?
Step 1. They start with diagnostics. The very first step is utilizing hyperlocal data, thermal satellite mapping, and street-level air quality sensors.
Acting like a doctor identifying the worst blockages.
Exactly. They locate the hottest, most polluted corridors, prioritizing areas around vulnerable populations like exposed schools, hospitals, and dense residential markets.
So they triage the city using data. That's step 1. What's step 2?
Step 2 is connecting the green space. Instead of throwing a random park into a neighborhood, planners have to map out a continuous pathway. They look at existing patches of green and figure out how to weave them together through the streets.
Abandoning the isolated park model entirely.
Yes, which leads to step 3, prescribing the specific vegetation and ground surfaces we talked about, permeable pavements and high transpiring trees.
I imagine this is where the interdepartmental friction really hits. If you are drawing a green line through the city, you are going to hit transit routes.
Which brings us to step 4, forcing the alignment of transport and greening. If the data shows that thousands of people are forced to walk, cycle, or wait for buses in a dangerously exposed heat island, the Transport Department and the Parks Department have to collaborate.
The green corridor must be routed to protect those specific commuting paths.
Exactly. And once the path is set, they can't just throw down some grass. It has to be a calculated scientific choice for that specific street's aerodynamics.
But none of this matters if the city abandons the project 6 months later. I feel like we see that all the time, a grand ribbon cutting for a green street, and a year later, everything is dead.
That brings us to step 5, and perhaps the most critical requirement of the blueprint, treating maintenance as structural design. A concrete pillar might just stand there, but a biosilic green corridor is living infrastructure.
It needs care.
Water-smart irrigation, soil care, and preening have to be baked into the municipal budget from day one. If the plants die, the climate infrastructure collapses. And step 6 is simply using data continuously to monitor the performance of these corridors.
So what does this all mean for you listening right now? We hear the term climate change, and it so often feels like this massive, abstract global issue.
Right.
We picture melting ice caps or rising sea levels decades from now. But what this deep dive really illustrates is that climate change is hyperlocal.
It is entirely immediate. It is the unnaturally hot asphalt right outside your front door. It is the smog you breathe in on the morning school run.
Yeah.
It is the invisible strain on your heart and lungs during a completely normal summer commute.
When a city follows this blueprint, mapping the data, breaking down the silos between departments, and engineering continuous biophilic corridors, it turns that brutal, exhausting commute into a manageable, healthy routine. It's about taking back the streets from the thermal trap of the concrete.
Redesigning cities to cool better, breathe better, and move better is not just about making a neighborhood look modern. It is fundamentally an intervention to improve human life.
Absolutely.
We're talking about reducing cardiovascular events, dropping the rate of asthma attacks in children, and making daily urban life livable again.
It's an incredible shift in perspective. To quickly recap our journey through the sources today, we started by looking at the physical anatomy of the urban heat island effect, how our low albedo, high mass concrete choices turn cities into thermal skillets.
Trapping both heat and deadly PM2.5 pollution, yes.
We realized that traditional isolated parks suffer from the edge effect and can't change the thermal behavior of a sprawling city, leading us to the necessity of networked urban green corridors.
And then we explored the design science behind those corridors. Evaporative cooling through permeable surfaces, airflow geometry, and biophilic integration.
And saw how cities from Singapore to Curitiba are already engineering nature into their operating logic. Finally, we saw how cities can execute this transformation by using thermal data to force collaboration across siloed government departments.
It's a comprehensive approach.
As we wrap up this deep dive, I want to remind you that the future of your city depends not on how fast it grows or how many high rises it can blindly build, but on how intelligently it is designed to manage and absorb environmental stress.
I want to leave you with a final thought to mull over, drawing from everything we've covered today.
Go ahead.
If our current urban environments are essentially master classes in trapping heat and pollution by design, what if we started looking at every new slab of solid concrete poured in our neighborhoods, not as inevitable development, but as a design flaw waiting to be challenged?
A design flaw waiting to be challenged. That reframes everything. The next time you step outside and feel the heat radiating off that cast iron skillet of a sidewalk long after the sun has gone down, I hope you look at your daily commute through this new lens of urban climate infrastructure. Thanks for joining us on this deep dive.